time to go ahead and get started with our afternoon session. Our first speaker this afternoon is Cynthia Rudin. You already heard her say a little bit of stuff about what she does this morning on the panel, but now she's going to be telling us more about machine learning for creating scoring systems.
Thank you. Okay, so this is joint work with Burke Wheaston, and who's my PhD student, and Jiming Zheng, who was an undergraduate working with us and is now a PhD student. And I'm just going to put up the stuff from the ProPublica article that was talked about earlier, where you have this risk scoring system that has.
Sorry, could you get the microphone closer?
Hold it. Okay. So with this young black woman who has virtually no criminal history gets classified as high risk, whereas this like seasoned criminal who likes to commit armed robberies gets a low risk. So we know the thing's biased, but it's really hard to figure out what exactly is wrong with it. And there's this beautiful article by some people who may be here in this room who says, well, the system might still be biased, but we can't tell. And it's because the company Northpoint refused to disclose the details of its proprietary algorithm, making it impossible to fully assess anything. That's understandable. Northpoint needs to protect its bottom line. No, it's not understandable. We should not be protecting Northpoint's bottom line. We should drive them out of business. Anyway, so luckily the traditional, these guys are actually very non-traditional. The traditional way to solve this problem is with a scoring system. This is a scoring system that was designed in 1928 for determining what success or failure of parole. And you get points based on things like whether you're a ne'er-do-well, a mean citizen, a gangster, or a farm boy, whatever. So you add up the scores, and then that's your risk score. It translates it into a risk of your success in parole. Okay, and these scoring systems have been used since 1928, and in particular, they're used all over the place. And at least 20 states have implemented the practice of using evidence-based risk scores in sentencing. I'm not claiming that risk scores should be used for sentencing. I'm just saying that people are doing this. This is one of the current scoring systems that was designed by the Pennsylvania Commission on Sentencing that's in use. Here's one from, this one. Yeah, so this gives you the probability of being arrested within a certain amount of time after being released. And then this one is for violence risk, and then your score translates into either a low, medium, or high risk category for violence. Now that kind of begs the question whether or not there's a principled way to create these scoring systems. Should we just have experts create it like we've done since 1928 and then just validate it on data afterward? Well, that's one way to do it. You could just ignore all the data when you're creating the thing. Or should we do what some of the sort of more modern people do, which is manual feature selection, and then you do logistic regression and then round the logistic regression coefficients? Right, this is what all the doctors are doing, all the kind of computer science-y doctor types. Anyway, so we could do that, but this is kind of a hack. And if you round points in a high-dimensional space, you could really mess things up. Like if you have a lot of very, very small coefficients, they all get rounded to 0, and then you lose that whole part of the signal. So rounding in a high-dimensional space, bad. Okay, so maybe we could actually try to solve this problem. And the main point of this lecture is that our machine learning tools and skills can really help with this problem. Right? We're not looking for pretty theorems here. We're actually trying to solve the problem. Okay, so this is SLIM. This is super sparse linear integer models. And SLIM minimizes a combination of false positives and false negatives. So these are accuracy terms. And then it tries to make the model sparse with the L0 penalty. So L0, okay, make it sparse. And then this term over here makes the coefficients coprime. So the coefficients have got to be integers. And when you include a very tiny L1 norm as a regularization term, it doesn't influence accuracy and it doesn't influence sparsity. It only influences making the coefficients co-prime. So when I say co-prime, I mean that if the scores were like 2 points, 2 points, 4 points, 2 points, 6 points, if you have that tiny little L1 term, they turn into 1, 1, 2, 1, 3. And it provably doesn't affect accuracy as long as epsilon is below a specific threshold. Okay, SLIM has a bunch of major advantages. Okay, so how much training accuracy do I sacrifice to get one fewer term in the model? How much is it worth to me in accuracy to reduce the model by one term? You can't answer this for logistic regression or any other method, but here you can. It's just C0. It's very easy to prove. How much training accuracy do I trade in this method to get the coefficients to be co-prime? Right? Usually the L1 norm is to try to help you make things sparse, but here it doesn't. It just makes things co-prime. So how much training accuracy am I sacrificing to do that? Now, because I'm using the 0,1 loss, the answer is provably none. Okay? As long as epsilon is below the amount that the accuracy term or the sparsity term, reducing either one of those by, then you will sacrifice no loss for getting coprime coefficients. Could there be a sparser model with equivalent training accuracy? Now, if you actually solve this, you have a certificate of optimality, and the answer is provably not. Okay, you're getting the sparsest model for the training accuracy that you got. Now, you could say, fine, well, Cynthia, it's NP-hard. You know, you're a computer scientist. You should know that we should never solve NP-hard problems. Now, NP-hardness, excuse me, but NP-hardness means that there is some particularly bad problem in the world for which I would have a very, very hard time solving this. But those are not the problems that I'm actually solving. If you actually design your cuts properly and you do good branch and bound for many practical problems, you can solve this. Okay, can I get a model that's optimal for a particular point in the ROC curve? If I'm making a particular, if I care about sensitivity more than specificity, if I want the particular point on the true positive, false positive trade-off, can I get that? And the answer is, of course you can. You just put in a constraint into this model that says, give me the best true positive rate for a given false positive rate. Okay. If you did lasso and then you rounded coefficients, could you get the same thing? And probably most of you think the answer to this is going to be yes. But the answer is no. And in fact, it can be a lot worse, and you don't have any guarantee on how much worse it actually is. Now, this is the mushroom data set that everybody in this room who's done machine learning has experimented with the mushroom data set. And this is model size on this axis, test error on this axis. Model size small is better. Test error lower is better. So you want to be down in this corner of the thing. And this is the lasso in red run through its entire regularization path. Okay, so lasso tuned to every possible parameter value. And you get these curves here. Actually, the one on the top is the one I need to look at, because that's training accuracy. And then the SLIM model is the one in blue. And you can see that it's sort of uniformly better than the lasso model. Okay, so even though this is a data set that you've worked with over and over and over again, you didn't know that there were better solutions out there because you never tried to solve them, find them. And it generalizes very nicely. So the top is training error, and the bottom is test error, so out of sample error. Okay. Now, somebody said to me the other day, oh, but I want to use lasso plus rounding because it's simpler to explain to domain experts. Absolutely not. I mean, lasso is a computational, it's a trick to make things convex so that, that it's computationally easier. But trying to explain to a judge or a police officer why I did this approximate thing is not easier to explain than simply to say, no, I'm actually optimizing accuracy and sparsity at the same time. I mean, computational hardness, this is, as I said, this is our problem. It's not their problem. By making them deal with it, we're not doing our jobs. Okay. Do I need to tune the parameters? No, you don't, because all you got to do is decide how much training accuracy you're going to sacrifice to get one fewer term in the model. You call that C0 over there. Or you could just tell it, I want a model of size less than 5, and you can put in a constraint that'll do that. And then you just set epsilon sufficiently small, so below this particular value, and you just run it. I mean, if you're going to run some other method over and over and over again to tune parameters, you're getting to the point where you might as well just use this method, and it's actually computationally faster. Okay, and then if you really do care about theorems and so on, the slim generalization bounds are actually quite tight because the set of coefficients is actually small, and that reduces your the complexity of your feature space. Also, there are these data reduction bounds that actually allow you to chop off parts of your data that don't actually influence the final model you get, and then you can work with a much smaller model. And then also you can prove that under certain conditions, the fact that you're using discrete coefficients actually provide no loss in training accuracy because the discretization is farther than the distance from the margin of the minimum margin to the decision boundary. And as I showed you, it tends to generalize well. So here's the slim MIP. Okay, this is a mixed integer program. It goes into a solver, and you solve it, and that's it. So we took this method, and we applied it to the largest data source, a publicly available data source on recidivism. And this is a big data set with 33,796 prisoners. They were all released in the same year. It's about a third of the prisoners released in the United States that year. We have a whole bunch of data about each prisoner. We know their gender, whether they were a drug abuser, alcohol abuser, their whole criminal history, all kinds of what they did in prison. Did they have any fights in prison, and so on. And then we aimed at 6 prediction problems: whether they were going to be arrested within 3 years of being released, whether they were going to be arrested for a drug crime, whether they'd be arrested for a violent crime, domestic violent crime, sexual violence crime, or fatal violence crime. So let me show you the results. So these are the RSE curves for the prediction of arrest within 3 years after being released. And as you can see, all of these curves look the same. And these are curves for all of the different machine learning methods that we could get our hands on. Okay? The only one that's a little bit weird is the green one, which is the CART model. CART tends to do a little worse than other things. Also, C5 and C4.5 tend to do a little worse. The SLIM models are in blue, so they perform just the same as everything else. And they're nicely distributed across this RSE curve, as I'd like you to notice. There are models all the way along the RSE curve. If you would like a model at any point in the RSE curve, you can just get one. So this is the RSE curves for general violence. And again, the decision tree methods don't perform so well, but everything else pretty much performs the same. And you get nice blue dots all along that curve. This is sexual violence. Again, same deal. So let's go back to the arrest curves. Now, each one of those blue dots is a model that we optimized for using this MIP solver and the SLIM formulation. So let's take a look at what that model actually looks like. And there it is. I can put it on a slide. I don't need to be proprietary about what predictions it makes. This is the model. That's the whole thing. It says predict arrest for any offense if the total score of the person is greater than 1. They get 2 points for being young when they're released. They get 2 points for having lots of prior arrests. They get a point for misdemeanor. They lose points if they're older or if they don't have any prior arrests. It's very simple. And then once you have that model, if you don't like that sort of point score thing, you can actually turn it into some logical conditions here, which you're probably trying to do in your head already. So the model basically says, predict that they'll be arrested if they're young, or they have lots, big criminal history, and either they're not too old when they're released, or they were older, but they have misdemeanor crimes. Okay? So that's what the model says. Now, if I took the same points on the RSE curves for lasso and cart, I get models that look like that. And I'm not even going to try to explain to you what those models actually say, because the number of terms in those models is too large for my brain to handle, because I'm only a human, and humans can handle 7 plus or minus 2 cognitive entities at once. Okay, so then we tried taking lasso and cart and restricting them to have model size less than or equal to 8, which is the number of terms that we have. And what we found was that even if you run across if you tune the parameters to every possible setting, there are certain points on the RSE curve that you just can't get. So here, all the models are bunched up over there, and there's nothing we can do to get a model down here. The method just can't produce one. It's just not capable of it. And that's very sad, because you just, no matter, you start fiddling with it, and you're like, this is Burke and Jermaine going, but I can't get a model on that part of the RSE curve. It's like, well, yeah, you can't. Okay, and then also, even if Lasso and SLIM do produce equally accurate and equally good models, which they do sometimes, then they're still not quite equally interpretable, because, like, the points, the fact that these are points makes a big difference. Like here, it's really hard to add up these numbers in your head and like really understand how these variables relate to each other when, you have to add up all these things and try to figure out what's actually going on. Whereas with just 2, 1, negative 1, it's much easier to deal with, just mentally. Now, I can't imagine a judge having a calculator right there. Okay, so let me show you a few more of the SLIM models. There's one for domestic violence. And again, it's just, you can put it on a slide there. This is genital violence, sexual violence, fatal violence. Okay, so now SLIM is nice, but what if we want, instead of just a decision, what if we want a risk assessment? Okay, so the difference, so the top one is from SLIM, and the bottom one is from this new risk assessment tool called RiskSLIM that Burke has been building. And the difference between these two is actually here. You can see, predict arrest if blah, if the score is greater than a threshold. Whereas in the bottom one, it's like a traditional risk scoring model where you calculate the score, and that translates into the risk of being arrested. Okay, so 2 fundamentally different problems there. So let me tell you about the method that produces this model. Okay, so that is designed to minimize the logistic loss combined with the L0 norm. Now, the logistic loss, you don't need another term to do the coprimeness, because the logistic loss handles making those coefficients smaller, so you don't need that. But I'm sure that some of you complexity people in the audience are looking at me going, Cynthia, what are you, nuts? This is a mixed integer nonlinear program. You can't solve this. It's going to take you to the end of the universe to do it. And I can say, no, that's not true. That's not true at all. In fact, we can solve it for data sizes, arbitrarily large data sizes. Not necessarily arbitrarily large feature sets, but we can solve it for very, very large data sets. Now, the only reason we can do this is because we have specialized optimization techniques, and in particular, a cutting plane method a particular cutting plane method. So, in case you're not familiar with cutting plane methods, let me tell you how they work. So, we start with some solution. Let's call it lambda 1. Start with that guy. Then we evaluate the objective at that point, and we produce a gradient, and this is called a cut. We know that the solution should be better than this, okay? And then we also know that the optimal objective value has got to be above 0. So we know that it's got to be above this. So we'll use this one as our next guess for what the optimal solution might be. And then we'll do the same thing. We'll evaluate the objective and get a cut. And we keep going like this until we And we actually optimize, right? We're going to optimize this thing right here, just the cuts, the surface that's formed from the cuts, and then that'll be the solution right there. And this turns out, yep, we'll just keep adding the cuts until what happens eventually is that we'll find out that our lower bound, which is made of those cuts, is actually equivalent to the value of the objective. And then we say, okay, we're done. We're done. We know that there cannot be a better solution. Now, the nice thing about these cutting plane methods, and the reason they've been so successful for support vector machines, is because of the way they handle data-related computation. Now, the way they do it is that the cycle here is that the cutting planes are generated from the data, those cuts, and then the collection of cuts goes to the solver to minimize the objective. So the solver never actually sees the data, which is why it works so well. So in other words, if you're right there, to calculate this cut, you use the data. But then the solver just sees that and minimizes with respect to those cuts. So that's why you can scale to these huge data sets. And it's been why it's been so successful for support vector machines. But you see, this would work all nice and well if our problem was just like this, but it's not, you see, because our optimal value might be over there because we're working on the set of integers. And so this is not a feasible solution for us. Now, the problem is when you do that, the problem with this is that as you add these cuts, right, you're adding more and more cuts and sending it to the solver. And if you have 200 cuts or something like that, and you send it to a MIP solver, it's going to choke. Like, what happens? This is time per iteration, so time per cut, number of cuts, and this is iteration number. And you can see it's okay. It's after a while, but then after you add like 70 cuts, it just is like, no, I just can't. No. And the optimality gap, which is supposed to go to 0, just stays up at 100%, and you're just stuck. So RISC-SLIM uses a new cutting plane method. And what it does is it solves the linear program and doesn't worry about feasibility. And then it says, OK, well, let me just put the function up there. It says, fine, I'm not feasible, but I know that it has to be an integer. So I can block off this whole area here, anywhere near me, and then I'm going to handle each piece of this separately. But if I actually happened to get a feasible integer point when I solve the LP, then I'm in very good shape because I can just add another cut. Okay? So that's how it totally avoids this issue we had with the stalling in the other method. And so where we had stalling before, now all the stalling goes away. And since we're solving an LP rather than a MIP every time. And then we can solve it for, this is 10,000 iterations, and the optimality gap starts dropping all the way to 0. So that's very, very nice. And this is the total runtime. So this is 10 million observations here. So 10 million people escaping from prison. And you can see that the total time increases, but most of the time is spent just calculating the function and the gradients. And the solver actually doesn't choke at all, and it can keep running. Okay, so that's really the sort of thing I really wanted to get to, which was that now, we have these tools, we can calculate these risk scores. I don't know. I think that we should force these companies, if they're going to give, risk scores without any reasons or explanations, they had better prove to me, at least, that there's no smaller model that can get just as accurate. Okay, so I'm just going to put up Berk's new ADHD scoring system so you can all figure out whether you're ADHD while I summarize the talk. So, okay, we can build scoring systems directly from data. Humans do not need to fiddle with the parameters to construct it. It might not be perfect, but at least you can figure out why. if the scoring system gives a score and it doesn't make any sense, you know, if it's an issue with the data, you'll know about it. If it's an issue with the scoring system, you'll know about it. Okay, so thank you very much.
Time for one question. So if anybody would like a question, please go over to the microphone. Okay, I will ask a question. I suppose I will go over.
Good microphone.
All right, good. Hi. My question is, have you shown this system to decision makers? And if so, what were their responses? And did you show them the system in comparison with some of these other systems that are maybe less interpretable?
We've been using SLIM for years now. I think, Burke, how many papers do you have written with doctors? Probably 3 or 4 papers. Yeah. So, I mean, the doctors, they love it. They're thrilled.
That's
because you can-
awesome. Okay,
yeah.
good.
I mean, we always write papers with the domain experts so that we know
Got it.
what's going on. Yeah.
Okay, great.
Okay,
Thank you.
sure.
All right, let's thank Cynthia again.
Oh, good, thank you.
All right, so we continue the discussion on explaining decisions of machine learning systems. I'm Anupam Datta, I'm at CMU. This is joint work with my student Shayak Sen, who's here in the audience, and Yair Zik, my former postdoc, who's now a professor at National University of Singapore. So Shayak will join us for the Q&A. He deserves a lot of credit for the work. If you have hard questions, he's your man. Machine learning systems are often opaque, not the ones that Cynthia talked about, but many other kinds of classifiers that are used. A user is denied credit, and there is no explanation for why. Or for recidivism scores, there's no explanation for why that particular kind of score was assigned. And this kind of opaqueness can also be a problem from the standpoint of discrimination if there is systemic bias and one group of users is treated very differently from another, let's say based on gender, then also we would like to know why these decisions were made. And so the specific question that our work tries to address is how much influence do various inputs or features have on a given classifier's decision about individuals or groups. So this is in contrast to Cynthia's setting, where she's training the model, and she's training it in a way that the resulting model is interpretable. We have no control over the training algorithm. Someone has applied some complex method to train the model. We are now trying to explain, given a model, why it's making certain kinds of decisions. So as a concrete example, imagine this individual who has these features, and this particular person was denied credit. Then our explanations would be of this form, where we want to say that some of the factors, like their occupation and education level, were highly negative factors which resulted in the denial, whereas other features, like their capital gain, was a positive factor that could have resulted in them getting credit were it not for these other negative factors. So the question is, how do we generate these kinds of explanations in a way that's systematic, that with some firm foundations behind the explanations. So our result is these quantitative input influence, or QII, measures, which are a family of measures of feature influence in classification that I will describe in this talk. And in ongoing work, which I won't have time to get into today, we also show how these QII-based features can serve as a building block for notions of discrimination and privacy, and for enabling accountability. That is, given an instance of violation of privacy or discrimination of this form, we have algorithms that can explain why those particular forms of violations emerged, and also algorithms that can be used to repair the models to avoid future violations of those forms. So I won't have time to talk about the second set of results. I'm going to focus entirely on the first part of our results in this talk. So let me first highlight a couple of challenges in generating these kinds of influence measures. So imagine this setting where Joe goes in, his data is used to make a decision about him, and two of his features are provided as input to the model, age and income. This is a particularly kosher classifier that only looks at income to make the decision about credit. It does not even touch age at all. So now if we were using some measure of association or correlation as our candidate measure, then let's say high-income individuals get positively classified by this classifier, but since age is positively correlated with income, we will also see a strong positive association between age and the decision to get credit. So in this sense, the measures, simple measures of association, are not sufficiently informative, because using income to make decisions about credit would be a perfectly kosher use, whereas the use of age would be problematic. If you want to get an even more explicit example, replace age by race there, and let's say there is an association between race and income, we want our measure of influence to be able to separate out these cases where income is directly used and race might be indirectly used, because income in this case is a proxy, but this would be one example of a proxy use which might be quite acceptable in this particular setting. The second challenge that I want to address is that we don't just want to provide explanations for individual outcomes. So in addition to being able to explain which input had the most influence in my credit denial, I also want to answer questions of these other forms. So what inputs have the most influence on credit decisions of women, for example? Or what inputs influence men getting more positive outcomes than women? So this whole broad swath of queries we would like to be able to answer with our measures. To address these two challenges, in defining our notion of QII, we will rely on two key ideas. The first is a notion of causal intervention that will deal with the first challenge of correlated inputs. And the second is a notion of quantity of interest, which will be our way of capturing or supporting a general class of transparency queries. So let me give you the key ideas behind these notions. So when I say causal intervention, the way I'm going to measure the influence of a feature is by keeping the one feature fixed and varying the other in a specific way. So if I want to measure the influence of age, for example, I'm going to keep income fixed and randomly sample age from the marginal distribution of age in the population. And I'll measure how often the decision changes as a consequence of that. In this particular example, you'll notice that if I keep income fixed, then randomly sampling age and varying age has absolutely no effect on the final outcome, which means that age has no causal influence on the outcome, which is the way it should be, in that it gives us a good measure of the influence of age, direct influence of age in this particular classifier. If in contrast, I want to measure the influence of income, then I keep age fixed and sample income from the marginal distribution of income in the population, and now I see that the decision keeps switching. And I can measure how often that happens as a way to quantify the degree of influence of income on the outcome. So in a little bit more detail, what we are doing here is comparing the behavior of the classifier on the real input. So X here is the real input, which might be the features of a particular individual Joe. And I'm going to compare it with the behavior of the classifier on this hypothetical or counterfactual input distribution, which is constructed from X and the population in a particular way, where I keep all the features fixed, except the ith feature, whose influence I'm trying to measure. And for that feature, I'm randomly sampling the value of that feature from the marginal distribution of that feature. So if this feature were, for example, gender, and in the training data set, or the population to which I'm applying this classifier, let's say 60% of the individuals are female and 40% are male, then the ith feature will be set in this intervention with probability 60% to female and 40% to male. And then I look at the difference between these two probabilities. On the real distribution, what's the probability that an individual this particular individual is positively classified, versus how does that probability change when I work with the intervened distribution? So that gives me a measure of the influence of the ith feature on this particular outcome for this particular individual. Now, we don't have to restrict our attention to that particular statistic. If we are interested in classification outcome of an individual, then that is the statistic we care about. But if you're interested, for example, in the classification outcome of a group of individuals, then we ask, how does the probability of being positively classified conditioned on being female change as a result of this intervention? And similarly, we can measure disparity between classification of outcomes of two groups by just varying the quantity of interest that we focus our attention on, right? So on the previous slide, the particular quantity of interest I was interested in was this one. And then if you're interested in other behavioral statistical properties of the classifier, we can set that to be the quantity of interest and see how that changes as a consequence of the intervention, to measure the influence of the feature on that quantity of interest. So now we have enough material to state the crux of the definition, which is that the quantitative input influence of an input I on a quantity of interest, QA of X, of a system A is the difference in the quantity of interest when the input is replaced with a random value via an intervention. So there are a bunch of things here that our measures are parametric in. You can pick different notions of interventions, different notions of difference measures, and different statistics or quantities of interest to focus on depending on what causal question you're trying to answer. So these are two of the key challenges that our work has addressed, but this by itself is not enough to give us the full power of explanations that we are after. So let me point out one very significant weakness of this solution, and that is single inputs will often have very low influence on the decisions of classifiers. And that's something we empirically observe in our experiments as well. But here's a very trivial example to illustrate the point. So here's a classifier which makes the decision to only accept old high-income individuals. And now if you apply the measure that I just described, that measure will always be very low. In fact, the individual influence of any single feature will often be just extremely low. So a natural way to generalize the previous idea is to, instead of talking about the influence of a single feature, we can talk about the joint influence of a set of features, right? So in the previous description, I was looking at how the quantity of interest change when you intervene on one feature. Now I'm just generalizing that definition to say, how does the quantity of interest change when I intervene on the set of features in S jointly? So now I'm going to sample that set of features jointly from their marginal distribution. So that's a step in the right direction, but that by itself is not a full answer because not all features are equally important within a set. So if I say that age and income collectively have high influence on the outcome, I'm not answering the more nuanced question of what's the relative importance of age versus income in the final outcome, right? So Another sort of more topical example would be that all the states that became red during the presidential election, their joint influence on the outcome was very high, but what was the relative importance of, say, Pennsylvania versus Texas on that outcome? That is what we are really after in order to give a more nuanced notion of influence. And to get towards that notion, we first consider this notion of a marginal QII, which is the incremental or marginal contribution of a feature towards a set of features. So if you look at this difference, so this is the joint influence of the set age and income. If you subtract from that the influence of just the set with income in it, then that gives you a measure of the incremental or marginal contribution of age to the set age, comma, income. Now, as you may have realized, if I focus on any single feature, it's going to be part of many different sets of features. So here are all the sets to which age can have some marginal contribution to, and therefore we need some reasonable way of aggregating the marginal QII notions across all these sets. And this is where we will rely on or build on or draw on some ideas from cooperative game theory and view the set QII as a cooperative game. So in a cooperative game, we have a set of agents, and so think of the set of agents as the features. Each feature is an agent in our setting, and the value of a set S is the joint influence of the set QII of that set of features. A typical example of a cooperative game is a voting game where the value of the set might capture does the motion pass if the voters in S vote yes. So if the voters in yes vote yes, then the value becomes 1. If the motion passes, otherwise it's 0. And the marginal contribution of the ith voter towards this set is the value of the set with I added to it minus the value of the set without I in it. In our setting, as I said, the input features are the agents. The influence of a feature set S is just the set QII, or the joint influence of the set of features, and the marginal QII is going to be the difference between a set with I in it and the set just without I in it. So once we have these preliminaries, we can define the Shapley value as an aggregation measure for, gives us a way of aggregating. The Shapley value gives us a way of aggregating these marginal influences. Mi of S is the marginal QII here of the feature I with respect to the set S, and notice that we are aggregating that over all sets. And this particular form of aggregation, there are many other choices of how you may want to do aggregation. It turns out that this particular way of aggregation satisfies a set of natural axioms. It's the only measure that satisfies a set of axioms that are quite reasonable in our setting. So I'll give you a sense of what these axioms are saying and what they represent in our setting. The first axiom is symmetry. Symmetry says that if two features have equal contribution, equal marginal contribution across all sets, then they have equal influence. So imagine that you take a feature in a database, you take a column, and you just make a copy of that column. It's a cloned feature which has exactly the same values. You would expect that both of those features will have equal influence in the final outcome. And that's sort of the intuition that the equal marginal contribution intuition captures. Dummy is another axiom that says that zero marginal contribution implies zero influence. So in this case, consider a feature that is an input to the model, but the model doesn't even touch it. So it's an input that's completely ignored, and that input should have no influence on the outcome. And that is exactly the running example. In my running example, age was such a feature. It had zero marginal contribution. It was a feature that was never touched by the model, and therefore, according to our measure, it has zero influence as well. And the third property is this monotonicity property, which says that consistently higher marginal contribution across games yields higher influence. So one way to think about this is that if I look at two individuals, me and Shayak, and let's say age consistently has higher influence on my decisions has higher marginal contribution for my setting than it does for his, then in the final scores that we get, it should have higher influence. H should have higher influence for me than it does for him. So these ideas can be translated into math relatively straightforwardly. I'm not going to try to work through this slide, but if you're interested, I'm happy to talk with you offline. The Shapley value is the only value that satisfies these very natural axioms, and that's the reason we pick it as our aggregation measure. Now, there are a bunch of other aggregation measures that might be more appropriate if we are not just interested in explanations, but explanations as an end in itself, but let's say explanations as a basis to direct action. So for example, if you want to say, give advice to people who were misclassified by a credit classifier, who were denied credit by a credit classifier, and you want to give advice to them on how they should change their input features in order to get a better outcome in a few years, then this will not be the right measure, because not all interventions will be possible. So for example, if the advice you want to give to that person is, well, you should reduce your age, that may not be an actionable advice. And that is sort of the crux of why this particular measure is absolutely appropriate if you want explanations as an end in itself. But if you want explanations with other ends in mind, then we have to adjust what particular measure of aggregation you pick. So let me briefly, how am I doing on time?
You have 11 minutes.
Okay, perfect. So let me briefly point out some of our empirical results from training standard machine learning algorithms on models on some public data sets. So in the first application, we constructed a predictive policing application that was using a slice of data from the National Longitudinal Survey of Youth. So there's a bunch of features in here about age and gender and race and location, smoking history, drug history, and so forth. And the classification outcome is history of arrests, and there are about 8,000 individuals in this data set. We also trained an income prediction classifier using a benchmark census data set. We are thinking of this as kind of a stand-in for, let's say, a credit classifier, which makes decisions on credit based on whether income is above the threshold of 50K. And so this is from the UCI data set, data from the UCI data set. And the particular data set we used had about 30,000 individuals. And we experimented with a broad range of machine learning models, logistic regression, kernel, SVM, decision trees, and decision forests, bunch of which are quite opaque. If decisions were not explained, it would be hard to figure out why they were making certain decisions. Then let me show you some of the instance-specific examples of explanations that we got from this system. So here's an individual who was denied credit, and we wanted to figure out what were the most influential features in this decision. And it turned out that for this particular individual, the education and marital status were the two most negative features. So on the right-hand side is sort of our informal explanation, right? So here on the left-hand side of the slide is the formal explanation, which comes from the QII measure from the Shapley value. And the way to read the left-hand side of the slide is that on the x-axis we have the different features, and on the y-axis we have the Shapley value. And if the value is positive, like in this case capital gain has a value of 0.4, that's the most positive factor for this particular, that's the most positive feature for this individual in terms of that played a role in the decision making. And as we go further to the right-hand side of the slide, of this figure, we have the negative factors here. So marital status, you see, is the most negative factor. Relationship is another negative factor. And one of the things that I want to point out in this case is that In some cases, these transparency reports, transparency is in some ways an end in itself, because when you're making decisions, you want to be able to explain why those decisions are made. But it can also serve as a building block to either provide evidence in support of a conclusion of discrimination or allay concerns about discrimination. In this particular case, and a concern that this particular individual might have had is that the fact that they were an immigrant, their country of origin or nationality was Vietnam, perhaps they thought this could be the reason they were denied credit, but in this particular case, we see that that was not a direct cause of the decision. So I'm not saying that it means that there is no discrimination of any other form. What I'm saying is that direct use of that, of the country of origin did not happen, which in particular assuages some concerns about formal disparate treatment, which looks at questions of explicit use of protected features, in this case, the country of origin. Now the second, here's another individual who is also an immigrant who might superficially look similar. And now when we run the explanation, generate the explanation for why this individual was denied credit, we get a very different explanation. So now it's the occupation which was the most significant negative factor behind this particular individual's classification. So explanations for individuals who might appear superficially similar can be quite different. You'll notice that this individual is from Mexico, and both this individual and the one on the previous slide are immigrants, but they were denied credit for different reasons. So in terms of related work, there is a fair amount of work on influence measures. There's a body of work on randomized causal intervention, which has in particular been motivated by questions of feature influence that are quite close to our causal intervention idea. The permutation importance work of Brayman is the earliest reference that we found to this idea. And in that work, they're using it as a building block for feature selection rather than as an end in itself, rather than as a building block for transparency reports like we are doing. So these results can be viewed as instances of our transparency schema. While the causal intervention idea appears in this work, they do not consider notions of marginal influence or general quantities of interest. There's also a bunch of work on associative measures. Associative measures are useful for getting at notions of indirect use or proxy use. So what we capture here, what we focus on, is direct use. The associative measures, to their strength, also captures potential indirect use through proxies, where instead of explicitly using race, you might be using zip code as a proxy for race. On the other hand, they lose track of the causality. And as I pointed out, that additional information is useful because it's important not only that proxies of race or some other protected feature are being used, but also which proxies are used and whether those proxies are in fact, whether their use is kosher or not. In my running example, if income is a proxy for race or age in decisions about credit, then it might actually be a proxy use that's quite kosher and acceptable. And to get at that additional level of information and insight about the use of proxies, it's important to capture this notion of causal influence. In fact, we see that in the law where we talk about business necessity defenses, which allow for exceptions. And this would be one way of getting at the core of that idea of business necessity. There's also a whole body of work on interpretability by design, and we have heard from Cynthia. Many of these methods, that's a completely complementary approach where we are trying to redesign the systems. In some cases, like Cynthia showed, we can get interpretability and accuracy at the same time, but there's also some cases where you don't. And that's really the big trade-off between going after interpretable models versus models that are being used in the wild without having interpretability. And there is the next talk will be on this other other body of work on interpretable approximate models that Samir will give. They can provide richer explanations. They provide a form of explanation that we don't. In fact, the whole body of work on neural networks and deep neural networks in particular demand a different kind of explanation than what we can currently provide. We are assuming that our input features have semantic meaning that's accessible to humans. So we are talking about features like age and income and zip code and so forth. But if the input features are things like pixels, then by itself, single input, measuring the feature of single input does not make sense. If the intermediate layers of the neural net have semantic meaning, then we could still apply these kinds of methods. One of the nice things about the next paper that you will see, next talk that you will, I'm sure Samir will highlight, is this kind of abstraction of an interpretable space, which I think is a really nice idea. But the causal relation in that work to the interpretable space, between the interpretable space and the original space, sort of remains unclear, and maybe that's a question we can revisit after your talk. So let me wrap up here. The quantitative input influence measures that we provide have these three key ideas as building blocks or elements: the idea of a causal intervention to deal with correlated inputs, quantities of interest to support a general class of transparency queries, and then ideas from cooperative games to measure joint and aggregate marginal influence of features. And also the nice thing, which I didn't get time to get into in today's talk, is that while these measures are wildly inefficient to compute exactly, they can be approximated efficiently, and they can be very accurately approximated efficiently using sampling methods, and so they actually scale quite well. So let me stop here and open up for questions.
I'll do it quickly.
Okay.
So I wanted to clarify what I think is maybe a slight difference in perspective between the work on the proxy influence things. I think, as you mentioned, the whole idea of the proxy influence-based measures is that you want to get at these things where things are correlated and different features can interact with each other. Well, one feature could be sending signals through another feature, and that could be used in the classification. And I think the issue of whether one is capturing causality or not, I think could also be interpreted as saying that in your approach, you're using a certain kind of prior for your random perturbation. In this case, in the particular example you mentioned, you have this kind of uniform prior over the marginal, right? Or prior over the marginal. And at least in the Adler method, which I know about, that's our thing, is that you use a different kind of perturbation method, essentially, to get at what you might think is the proxy influence. So then the discussion then becomes, what kind of priors are you using and how is that going to affect the way in which you measure influence? I'm not convinced, I could be convinced, but I'm not yet convinced that it's a difference between causality and not causality. But that's just a comment that, I thought.
Yeah, no, that's a great question. I think the proxy use, in my mind, the proxy use question still requires more exploration and discussion. And the way that we have been, that Shark and I and our co-authors have been thinking about this problem is on this slide. So we have these intermediate features. Let's say we want to check if some proxy for race is being used to produce credit offers. Then the way we are going to think about this is whether this is the machine learning model, that's the box, and the red triangle in there is a sub-computation whose output is the proxy. And what we mean by that being a proxy is that it's a strong predictor, it's strongly associated with race, and that it has a causal effect on the output, which is measured by the QII. And now this is different from your work on proxy use in that you don't look inside the model, right? You're looking from the outside. So we have a different access level. We are assuming greater level of access, which sometimes could be a weakness because we may not have access. But it's the internal testing setting that we are working with. And then this can distinguish and discover proxy uses in settings where with purely black box access, along the lines of what you are doing in your work, you will say there is no proxy use. So that's sorry to spring it on you like this, but I think the whole question of what it means to use proxies is far from being resolved. And it's an open question for this community to continue having a conversation on.
Hi, everyone. All right, let's get started. Great. So hi, I'm Samir. I'm a recently joined professor at UCI. And this is work with Marco, who's a PhD student, and Carlos, who's not a PhD student. Yeah. So a lot of background material has been covered by the great talks before mine, so there will be some redundancy, but hopefully not too much. Okay, so let's start with something that all of us understand, the fact that machine learning is everywhere. It has been helping us save time by filtering out our spam and so on. And it's been helping us save further time by playing all these games for us so we don't have to. And then with all of this time, now it's telling us what to do by recommending movies and stuff to watch. It is in our phones, it's in our house, and soon it's going to be in our cars, right? So great, machine learning is everywhere. Now, it's pretty easy to yourself go home and do some cool machine learning stuff. So this is what my student did in a couple of hours, which was train a classifier that can differentiate between a wolf and a husky, right? And so these are some example predictions. You can see that this classifier is actually pretty good. It makes one mistake, but this is much better than what I would be on this task, right? These two things are really similar to each other. But this is something my student trained. It's impressive, but let's keep going. The state-of-the-art deep learning stuff has these really cool visual QA kind of things, where you can ask questions, give it an image and a question to the computer, and it can come back and say, yes, there is a mustache in this image. And if you ask a more complicated one, what is the mustache made of? It's made of banana. So this is really cool. It seems to be doing something really smart. It's looking at the image, looking at the text, and combining all of these things together, and that's great, right? But the question is it doing exactly what we want? I mean, these examples are impressive, but that's not all there is to it. Especially if you have some crazy structure like this, a neural network, this is maybe 20 years old or something. We still don't know what it's actually doing. But you can also go and look at Google's neural network. This is like 27 layers, I think, and I can't fit it vertically. I have to put it horizontally. And there's no way to figure out exactly what's going on in them, right? And also recently people have proposed neural networks with almost like 1,000 layers, which is just, my mind boggles at that. And so essentially these are black boxes, right? And so especially for this workshop, they may actually be black boxes. We may not have access to them, but even if we do have access to them, it's too complicated to work with. And so there are a couple of issues that become pretty prominent when that's the case. You don't know whether you can trust these systems or not. You don't know whether the predictions are correct or not. They're just predictions. You can't really predict the behavior of machine learning models. So you can't say, okay, it's making these kind of mistakes, it's not making this kind of mistakes. So if I deploy it in real world, what's going to happen? And finally, we can't also improve the machine learning model till we realize what mistakes it's making, what it's doing, what it's not doing, and so on, right? So a couple of example cases of why this is important is when I showed you this figure and you saw only one mistake, hopefully most of you were pretty impressed by that. I was when we got these results. But what I actually did, and what my student actually did, was built a snow detector. So all this is doing is looking at the snow in the image. If it sees snow, predicts wolf. Doesn't see snow, predicts dog. That's also not easy to do. You can't just write a decision tree to do this, but it's still not as smart as we think it is, right? And now the mistake also makes sense. There's snow on the ground, it's predicting wolf, right? And this is what happens when you start deploying these things in the wild. Obviously, this guy didn't use the classifier, but yeah. Okay, but let's go back to the other example. This one is the one that's published, that's real. And I'm not trying to sort of disparage them. This is just something you do when you look at the output of the system, right? So you asked this question, and it said banana. And so I was playing around with this, and I thought I'll try out a different question, which was, what are the eyes made of? It's a banana. I'm like, okay. Well, I don't know how that's possible, but let me ask it more questions. What? It said banana. So it's getting the plurality correct, I guess. Eyes and bananas and what is banana. You can ask it what is, and it says banana. Right? So again, it's not doing something as smart as we think it is doing. We can't deploy this in the real world and expect it to do magic for us. It is doing something smart. It is realizing there's a banana. It's an object that is a decent response for what and maybe what eyes are made of, right? Okay, so given these things, what we are proposing is an explanation for each prediction. So I'll give you an example of what that looks like for a simple case. So this is a document classification task where we are given an email and we want to predict whether it's about Christianity or atheism. Right? And this is what the machine learning model gives us. It says, with a high probability, this email is about atheism. And this is clearly wrong. So a good question might be, well, what's happening here? Why did this happen? Right? And what our explanation tells you, very similar to Anupama's work, is what is important about this input in order to predict the classifier, right? So for example, we can just draw a bar chart with atheism and Christianity on one side and the other, and we're basically going to highlight words and their importance. So Christianity was supposed to be really important, and for the correct class. So Christians use Christianity. Right, wonderful. But then something weird is happening. It's picking up on the fact that there's some artifact in the email as an indicator for atheism. And you can kind of go down this list, and it basically, you see a bunch of these that shouldn't correspond to, the name Keith shouldn't correspond to being an atheist. And finally, you get one more, which actually is perhaps correlated with Christianity, right? So what we have done, and then there is one more, which is right? Which at that point, maybe it doesn't even matter, right? So this is the kind of explanation we want to produce without looking inside the machine learning model, and without just sort of looking at words instead of looking at what the feature representations of the model are, right? So now there are a couple of conditions that we want from these explanations. One of them is that it should be interpretable. What I mean by that is two things. When you think about decision trees and people say, oh, decision trees are interpretable, and by now we know that if a decision tree looks like that, that's definitely not interpretable. We want something that looks closer to this side. The other aspect of interpretable is what we are using to explain the prediction, and it should be something the humans can work with and have some semantic meaning to, rather than whatever features or embeddings the model is using. The second condition we have is also an obvious one. It should be faithful to what you're trying to explain. It's called an explanation because it should be an explanation. So if you have some complicated model like this, and you want, and suppose the user can't understand curves, you want to approximate it with a line, then this line is not faithful, right? Maybe no line is faithful, but at least this line is not faithful to what's happening. And finally, we want to be model agnostic, right? So the whole idea is that we should be able to take some neural network and be able to explain what's happening. And so to this end, we propose this LIME algorithm, which basically stands for Local Interpretable Model Agnostic Explanations. And the idea is that we pick a certain class of models that the users can understand. Right, so there's been a lot of work, and it could be lines, shallow decision trees, sparse features. It could be the SLIM representation. It could be any of those things, right? And the idea is then we're going to approximate the global model, the one that's really complicated, by these explanation families. And so if you have some crazy surface to your classifier that you don't even know about, what we are trying to do is pick the point that we want to explain. So suppose that's the red cross, and give a simple explanation for that particular point. Right? So if we are looking at all possible lines as something humans can understand, then this line would be the explanation for this decision. Okay. And so the idea here is that this model that we pick, it's not a good representation of the classifier overall. It doesn't say anything about what would happen outside of a certain region around the prediction. But for this prediction and other instances similar to it, it's really accurate. Okay, so the general framework, I just want to sort of write it out in math because some people prefer that. What we have is an instance that we are trying to explain. This is the family of explanations that we are searching over. It could be all possible lines, decision trees, anything. And then we're just trading off these two things. One is the faithfulness of the explanation. So in the locality around X, how good is our explanation to the classifier that we want to explain, which is denoted by theta here. And then some kind of interpretability measure, right? So how interpretable is this explanation to a human? So even if we are searching over decision trees, we don't want decision trees that are incredibly complex because nobody would be able to understand them, right? And so the first set of families that we played around with, and this is the stuff that we've studied most extensively, is sparse linear explanations. It's basically Lasso-style models. And the way we do that is we pick a point that we want to explain, and we sample a bunch of times around that point, right? And so we sort of perturb it in many different ways. And these perturbations are not across one of the dimensions that the previous talk was talking about. This is just perturbing any subset of features randomly, right? And so sometimes you get samples that are really far, but most of the time you get samples that are close by. But just to make sure that we are actually incorporating the locality, we weigh the samples according to the distance to the instance, right? So the closer you are, the bigger you are. So this is what it looks like. And we sent it through the classifier, and we have a blue or a red for each of them. And now it becomes pretty straightforward what to do. We just learn a linear model on top of these weighted set of samples, a sparse linear model. I can't show the sparsity in 2 dimensions, but yeah, that's the idea. Right? So let's see concretely what this looks like for images. Right? What we want to do is explain why this image, which is a dog playing a guitar, why this was tagged to be a dog. And so what we do is we take this image and we perturb it. Now we are not perturbing it in the pixel space or in the space that the neural network has or anything like that. What we're doing is we divide the image into patches, and we're just hiding a random subset of those, right? So that's, for example, one of our samples, and we do that again and again. And we send each of these samples through the classifiers, and that gives us a probability of the class that we're interested in. So for the first image, the classifier thinks this is 92% Labrador. So once we have these samples on the outputs, and these are about thousands of these, we can do a locally weighted regression to get a sparse linear model in terms of which patches are important and which patches are not. And that allows us to basically take the ones with the highest positive weights and visualize what's going on, right? So now this is an explanation for why this image was tagged to be Labrador. So if you just send this image to the classifier, the probability is going to be almost 1. Okay. And so what we've done is, we did this with Google's Inception neural network, and we can take an image like this and explain why it's an electric guitar. Well, it's because the neck of the guitar looks like an electric guitar, but that's what the neural network thinks is why this image is electric guitar. We can also explain why it's an acoustic guitar, and we can explain why it's a Labrador, which is an explanation we saw. Okay. So the neural network was actually wrong on this. It predicted the electric guitar with the highest probability, but it's such a confusing image that I can understand, I guess, sympathize with the neural network. But yeah, it's doing a somewhat reasonable job. Right? Okay, so let's go back to this example I had where I showed you we kind of faked this thing and we were actually detecting snows. And these are this is what the explanations look like for each image. You can see whenever you're predicting wolf, your explanation is basically capturing the fact that there is snow on the ground. And when you're predicting husky, it's not looking at the ground, it's actually looking at something else. But for wolf, it's basically snow every time you see it. And so that's what we wanted to do an experiment to see whether these kind of explanations are actually useful or not. So we did this experiment with machine learning graduate students and asked them, before we showed them an explanation and after we showed them an explanation, how good do you think this neural network is? And why do you think it's predicting what it's predicting? Right? And so this is what our results were. We did it over about almost 30 people. And we asked them, do you trust the model or not, before we showed them the explanation. And we asked them, why is it doing what it's doing? And just sort of we were pretty generous about this, but are they hooking onto the snow inside? Right? And so before explanation, about 60% of the people trusted the model, and about 45 or so people got the snow inside. But after they saw the explanation, almost 90% of the people did not trust the model anymore, which is good. I am curious about the 10%, why they still thought it was a good model. And almost all of them, even more than the ones who trusted it, got the fact that it was using snow. So there was at least one individual who thought that the classifier was using snow, but did not, but still trusted the classifier, which is interesting. So we did another set of experiments to see whether we can decide whether a classifier is good or not, right? So the idea is that these explanations should match our domain knowledge or our intuitions about the task. So if this is the image that we want to predict wolf to be, we want to predict it's a wolf. If an explanation looks like this, we can say that that's a bad explanation. But if an explanation looks like that, well, at least it's looking at the wolf, but specifically it's looking at the snout, it's looking at the eyes, and the ears, and the fur, so this might be actually quite good. And so what we do is, based on these explanations, without knowing anything else about the classifier, we can say that that's a bad classifier and that's a good classifier. Right? We haven't seen what the accuracy is, we haven't seen what the training data was, anything about the model. Just based on a single image, we have some intuition. So the question is, does this generalize to actual evaluation? So we did this with document classification. So this is an example explanation that our system had generated, which I had shown you earlier, which, as we saw, it was using a bunch of things that it shouldn't, and so we called this a bad explanation. And so in some sense, we shouldn't trust this model. Alternatively, this is an example of us generating the explanation. The colors are a bit different, but the green here means Christianity, the purple means atheism. And you can see that at least it's not picking up on random artifacts. The words seem to all be related to this question of atheism versus Christianity. Specifically, it's quite interesting to see God as the word being picked up by both, but with a lower case, it's more indicative of atheism, and with a higher case, it's more indicative of Christianity. Right? So this classifier is picking up on something about how we express these things, and so we can call this a good classifier. Right? Again, without looking at anything else. So we did some experiments with Mechanical Turk, where we showed them these explanations for two classifiers and asked them, based on these explanations, which one make more sense to you? Which one do you think you would trust if you had to classify your emails between atheism and Christianity? And the results were actually quite surprising. If you think about just guessing, it would give you 50%, but with explanations, 90% of the time, users were able to identify which model is better. And the way we define which model is better is in the paper, or I can talk to you offline about it. What was interesting was, for this particular setup, if you look at the accuracy of the classifiers, you would always get it wrong. So you would be 0% the way we had set up this experiment if accuracy was your only measure. So this was the stuff that we did earlier this year, and now we've been working on some newer things that I'd like to talk about. The first one is the fact that we have this problem with linear explanations as soon as we start talking about some tabular data. So for example, this is one data set that Anupam, like the previous talk, talked about. And you can see it has a lot of features, and you want to predict why somebody would have a high income or not. And so we had a classifier that was trained to do just that. And it predicted that this particular individual has less than 50K salary. And this is kind of the explanation. It's very similar to one we saw earlier as well. And so, it kind of makes sense. If you don't have much capital, you're probably not earning less. If you're not educated, if you're working less, your salary is probably going to be low. If your age is higher and if you're married, maybe those are correlated with income. So, yeah. But the problem is that these are very loose sort of correlations. Like we get the general idea, but it's not very precise. So in some sense, it's not what SLIM gives us, right? It's just sort of numbers, and you have to sort of add them in your head and do something. So what we were looking at was a slightly different question than the other talk so far. The question we had was, if we had the original input, what can we change about the input and still keep the same prediction, right? What is, of all those features, how much and what can we change them? And the feature doesn't change at all, right? And what that gives you is, again, a sort of fits into the LIME algorithm, where you're trying to still find explanations that are a set of constraints on your instance. And you want to find the constraints that don't change the decision for the distribution that they apply to. And these set of constraints are small so that you can still understand them. And we still want to do it in a way that neural networks we can do it on neural networks, we can do it on whatever we want to do. And so this is what it looks like for tabular data, even though this is what LIME produces. When we ran our constraint-based things, it says if education is less than high school, then salary is less than 50K. This just happens to be one of the simplest constraints because it involves only one feature. But the idea is that in a distribution around this instance, you can change all the other features as much as you want, as long as education is less than high school, you'll always predict less than 50K. This is specific to this instance. It's not a global statement we're making like SLIM does, but it does give you insight about what's happening. So we can do this with neural networks, which is where it becomes fun. So let's go back to this image, and we asked this image, if you remember, what is the mustache made of? And it said banana. And this time, what is highlighted? What that means is what seems to be the constraint that as long as what is in the question, the answer is always the same. So you can generate all these questions from our optimization that tells you that it doesn't matter what the rest of the question is, it always is banana, right? So this is a very nice way to understand what the neural network is doing, what it's focusing on, and so on. Similarly, we had another question, how many bananas are in the picture? And it said 2, and you can say that many is the keyword that it focuses on, and all of these questions that have many, it just gives 2. Right. Okay. Quickly, I just also want to give an image classification example. This is an image of a zebra, and this is the sort of set of constraints in some sense. What the constraints mean here is, if an image has this part, it doesn't matter what the rest of the image is, the classifier will predict zebra. And so we tried that out, and so these are all these other images which don't look real at all, but they are just this superimposed onto a bunch of images, and it predicts zebra with like 0.9 or higher probability, right? And you may agree or disagree whether that's doing the right thing or not. So it's not actually looking at the mouth or the legs or anything, it's just the stripe pattern. The last thing I want to talk about before I end my talk is this idea of using programs as explanation. This is very much in development. But the idea is that there are a lot of different models that people like to use for explanations. We have decision sets, lists, lines, and so on. But so many people know programming now that I was wondering whether we can generate programs as explanations, right? And programs are nice because they kind of generalize over all of these things. You can write all of these different things as pretty short programs. So the idea is, again, we are doing the same optimization, same stochastic sampling, but we are looking over a set of all possible programs. we are judging how good the program is in reference to the classifier that we are trying to explain, and then is the program short enough for someone to read. So we just have pretty early experiments on this. So this is a salary prediction problem that I showed some results on earlier. And these are the explanations that get generated for the same individual for 3 different classifiers: random forests and decision trees and linear models. And you can see that these are kind of different from each other in terms of complexity, and in terms of one of them is clearly just Boolean, other one looks a little bit more complex. And what we can do is we can also see whether this is the correct explanation or not for some examples. So for decision tree, we can actually draw it out and see what's going on. So what's happening is the blue path is the path that this individual actually used. And you can see both capital gain and married are in this path. But the path actually is more complicated. It has this education thing in there as well, which is kind of disappointing that our program doesn't capture it. But then you realize that even if you go down this other branch, you still get to the same decision. So our program is actually more compact than this already compact decision tree. Okay, so with that, I want to close my talk. I described what these model agnostic explanations are and how it's critical when we're applying these complicated models to be able to explain them. And I introduced this LIME framework, which, with linear explanations and with these prediction invariant explanations, and the current work on using programs as explanations. With that, I want to thank you, and please get in touch if you have any questions.
Great talk.
Oh, thank you.
I have a question for you. When you're doing the local sampling around the particular point of interest, are you concerned that the distribution that you're sampling on might not agree with the distribution of the population?
Yes, that's a good question. And we're trying to figure out ways to sort of formalize what that distribution would be in cases where what you're sampling falls out of the manifold of the data. Yes, so can we use a collection of large unlabeled data in order to sort of design the distribution to be closer to what the data is? But yeah, that's a good question.
For the visualizations on natural language, so in the examples you showed us, it would highlight the words that were the most effective, but you'd hope in more advanced classifiers that it would use grammars and things like that.
Right.
How would you visualize? Have you looked at how you would visualize more complex structures that it's picking up on?
Yeah, so that's actually one of the reasons why we didn't try more complicated stuff for NLP. It's the visualization question, right? So I think there is the optimization algorithm where if you want to find what the underlying grammar is for the neural network, maybe there's a way to solve that optimization. For visualizing, I think that's work that we would love to do, and that's cool. Yeah.
So I'm curious if you've thought about sort of the accessibility of the explanations that are being generated. I know you did some mechanical Turk experiments.
Right.
So it seems like people can kind of make sense.
Right.
But I wonder if you could sort of reflect a little bit on, for whom do you think these types of explanations are oriented, or do we need different types of outputs for different use cases?
So yes, good question. I think we definitely need different kind of answers for different kind of users. And in some sense, we want to have a framework that allows you to make that decision. And the question of what kind of explanations are useful for what kind of things is really, really exciting. If you want to improve the system, then maybe you need a different kind of explanation than if you just want to see whether it's good or not, right, for example. It can also vary between domains, so something that looks good for images may not work at all for NLP. And yeah, so I think with Mechanical Turk, these explanations do work, but the caveat there is that the level of performance of the classifiers is big enough. If they start coming closer, then you would have to give more fine-grained explanations in order to get at what's actually different. But yeah, that's a good question.
Great.
Cool, thank you.
I'm going to open a super secret demo video, and so everyone look away so you don't get spoiled for the surprise. I trusted you. So hello, I'm Sam, and this is work I've been doing with Laura Stantoni and Asa Bergudi from the University of Wisconsin-Madison, and with Aditya Nori from Microsoft Research. And so the reason we are all gathered here today is because in the modern era, algorithms are making decisions about people, and that's really cool, but it's introduced this concern that maybe the decisions it's making are biased or discriminatory. And so, if I'm going to use an algorithm to decide whether or not to give someone a job or something of that ilk, and you tell me like, well, here's this formalization of what it means for an algorithm to be discriminating against this group of people, what it would be great if I could do is if I could go like, well, no, this algorithm doesn't do that, and I can prove it, right? That I could have this proof of correctness about some property of my program. And the idea that we want to prove that our programs are correct in some manner is not new. It dates back into the early 20th century when Alan Turing, who you may have heard of, did stuff with computers. And so what he was concerned with is that people started writing these programs. And so what you can see here is a flowchart for a program that computes the factorial of a number. And people write this function, they say it computes the factorial, and you go, okay, but does it really? And so you either have to choose if you're going to take their word for it, or if you can find some sort of mathematical formalism that lets you, see, here's a proof, this function actually does compute factorial. And so the way that we reason about these kinds of things is that we talk about a precondition, which in this case is that you have a number n that's greater than 0. And what this precondition means is that, before I run my program, which is going to compute factorial, this is what I assume is going to be true. And then what we want to prove is called the postcondition, because it's something that we want to be true post executing the program. So in this case, what we say here is that when n is greater than 0, if I run my program, I want to prove that the return result r is actually equal to n factorial. And the way that Turing did this is that he takes this graphical representation of the program, and in a bunch of places he annotates things with logical formula, with the ultimate result being that you can take this logical implication, you can take the logical implication of all these individual parts, and they immediately imply this postcondition. And that is a rigorous mathematical proof that this program is correct. And so since then, one of the things that a lot of research has gone into in the verification community is figuring out how to automate this kind of verification process. And so the goal is to make these programs called verifiers that take as input both, some program that you care about proving something about, and then these precondition and postconditions that specify sort of the domain that you care about and the property that you want to be true. And what this verifier will do is that it'll return either that, congratulations, your program does satisfy this property, and here's a proof of it, or it'll give you some kind of bug or error. And you can use that to see why that your program doesn't satisfy the property. And so when Turing was working on this, they were concerned with correctness, and what it meant for an algorithm, what it means for an algorithm to be correct is sort of evolving, because as you have seen throughout the presentations today, you have algorithms that make decisions about people, and it's no longer just a correct algorithm if it's what the machine learning model should learn. We have these additional notions that the correctness needs to reflect a sense of fairness. And so, so our idea is that we're going to take these properties that mean fairness, and we're going to use them as postconditions to try to prove them. And so for example, suppose we have a decision-making program D, and it takes as input this vector V of features about a person, and it makes some decision about whether or not you should hire them. Our precondition is that we have this vector V of features that came from somewhere. This is what we're running the program on. And for a group fairness definition, we might consider the postcondition, or the property that we want to prove, to be that the probability that we hire a person given that they're a minority is roughly equal to the probability that we would hire someone given that they're not a minority. So, so the idea is that we're running this program on a whole bunch of people. And so what we're gonna say for this precondition is that we actually have some kind of population model, which we can think of as a generative program where you run it and it gives you another individual to run your program on, and that if you did this enough times, the population model would give you a distribution of people that matches the population you care about. And so if we were to prove this property, what we would be saying is that this program has this group fairness property for this population. So there are other notions of fairness. For example, we can encode an individual fairness-like property in this way, where we say that we get 2 individuals from our population model. And then if we were to run our program on each of them, the probability that the outcomes are different, given that the individuals were similar, would have to be pretty small. And so the point is that what we want to do is we want to talk about fairness properties in some language, and in our case, that language happens to be the probabilities of outcomes of the program. And so what we wanted to create was a general purpose framework where you could state fairness properties in this kind of language, and it'll take a program and a population model and tell you things about that. So we have a tool. It's called Fair Square. The logo is tentative, but I think it's kind of cool. And Fair Square is a verifier where you give it a population model as a precondition, the decision program that you want to reason about, and whatever that definition of fairness is, which is some arithmetic, some inequality over arithmetic expressions that have to do with probabilities. And what Fair Square does is that it either produces a proof that your program is fair, or that it is unfair, and how it does that is sort of what we're going to talk about now for the rest of the talk. But for a very concrete example, this is code. Surprisingly, we've seen very little code today, but this is what code looks like. And suppose that this is a function that we want to prove something about. It's a decision procedure that takes as input someone's college rank and their years of experience. And so what it does is that you can see with that first if statement is that if they're in a top 5 college, then it decides to hire them. Or otherwise, it uses this variable that it computes from the other variables and if that's beyond some threshold, it'll choose to hire, and otherwise it rejects you. And this is obviously a toy program, and you should not use this to determine whether or not to hire people. But the point is that this is comprehensible enough, and hopefully we can convey the big picture. So we're gonna, for purposes of illustration, try to prove a group fairness property here, that the probability that it hires you, given that you're a minority, which is represented as, we're pretending ethnicity is some continuously valued variables. So that the probability that it hires you, given that you're a minority, is roughly the same as the probability that it hires you, given that you're not a minority. And so to do this, we need to talk about what that precondition, the population model, is actually gonna be. And so an example of it is on the left, that we have the 3 variables that we sort of care about, the ethnicity, which determines whether you're a minority, and the college rank and the years of experience. And those are drawn from probability distributions. And there's an if statement inside the pop model definition that basically says, if you're a minority, then your college rank is worse. And this is just for this example how we're going to introduce correlations between variables. So the idea is that this population model returns, an individual's college rank and their years of experience, but there's an implicit correlation between their college rank and whether or not they're in the minority. So that even though the decision-making program doesn't anywhere explicitly access ethnicity, there's a redundant encoding. Because what we're going to end up looking at is this composition between the population model, which as our precondition spits out the inputs that we then feed to the decision-making program. And so when we prove the postcondition, we want to be looking at this composed program and reasoning about the probability of events happening within that. So in particular, if we want to compute probabilities, we have to do that somehow. In that postcondition, we talked about the probabilities of things having to do with hiring and minorities. So concretely, let's look at how you compute the probability that this program hires someone and that they're a minority. Fundamentally, we want to consider all the different people this population model could produce. And of those, some of those are going to be minorities, and some of those are going to be hired. And what we can think about is the set of the assignments that are made to those variables in the population model. Because recall that ethnicity, the college rank, and the years of experience are initially derived from probability distributions. And so what we want to do is we want to look at the set of those random assignments that would lead to first of all, them being classified as a minority, and then also the decision program choosing to hire them. And that's represented visually here in this graph at the bottom, where this space, if you sampled a point within that space and chose that as the assignments to each of the variables that are represented as each of the axes, then since the ethnicity is always within the range, that means they're a minority, there'd be a minority, and the rest of the region depicts the boundaries within the decision procedure that determine whether or not you're hired. And so if we want to talk about the probability that you're hired and a minority, then all we need to do is do some calculus. This is also the first integral to appear today, I think, so I hope that's not scary. But the idea is that each dimension is some variable that was drawn from a probability distribution. And so if we compute this integral over this region of the program space, where it's weighted by the individual probability distributions, what we get is a quantity that basically says, if I sampled a point at random following these distributions, what's the probability that it would lie inside this region that I care about? So if we do that for this, we're going to get the probability that we hire someone and that they're a minority. How we explicitly get these regions to integrate over is a little bit of magic, but it follows some pretty standard programming languages techniques. So I will hide the details from you. But there's this caveat that when we want to compute these integrals over arbitrary regions, that's a hard problem, and it's known to be a hard problem, and it really sucks to do it. So, but what's easy to do is to integrate over rectangles. And so one of the things that Fair Square does is that it pretends every region is actually just a bunch of rectangles. And so when we have, maybe we need to integrate over this triangle, we instead find a rectangle that's contained within the triangle, and we compute the integral over that. And then we get some concrete bounds. So specifically, this gives us an under approximation of the actual value of this integral. And we can use that to try to see if that postcondition is true. And maybe we don't have a precise enough approximation of this shape. And so what we can do is that we can get more rectangles and more rectangles. And we can do this iteratively until we've gotten enough rectangles that it's practically indistinguishable from the shape that we care about. So here's the example that we were talking about earlier. We have, as our precondition, this population model, and then we're going to run those inputs through this decision procedure. And what we want to show concretely is that the probability that the program hires you, given that you're a minority, divided by the probability that it hires you, given that you're not, is greater than 0.9. So if you think about it, since we have bounds on probabilities, all we need to show is that a lower bound for this quantity is greater than 0.9, and that's sufficient to prove this postcondition. Or similarly, we could show that an upper bound for this quantity is less than 0.9, in which case, the actual value is less than that as well, and the postcondition cannot possibly be true. And so here's the live demo. So initially, the tool runs, and it has to do that magical thing where we turn programs into formulas. And then what you'll see is that there's a series of upper and lower bounds that gradually get better every time we get more rectangles to get a better approximation of the probability. And so they get closer and closer together until one of them crosses that red line that denotes 0.9. And so once we see here that there's an upper bound of 0.8, we know that the actual value has to be less than 0.9. And so that's a proof that the program is unfair for this definition of fairness and with respect to this population model. I worked hard on that. I hope that was entertaining. So in summary, we made this tool called Fair Square that takes as input a precondition that's the form of some generative model that represents your population, a decision-making program, which in the example was just something I wrote, but you could think of this as like an actual instantiation of the code for a neural network or something of the sort. And it also takes a definition of fairness that has to be expressed in terms of expressions over probabilities. And then through this weighted volume computation magic, it produces a proof of fairness or unfairness, which ultimately comprises of the individual rectangles that it needed to compute volumes for to prove whether that the inequality was true or not. So we implemented this on a bunch of benchmarks that came from support vector machines and decision trees and a couple of very small neural networks from the same income data set that the last three presentations have talked about. And for many of them, it was able to produce proofs of fairness or unfairness for a group fairness definition of that sort. So yeah, I'll take questions.
How large, concretely, of a program can your tool handle? So you mentioned using very small neural networks, and obviously, like a deep neural network is going to have a much larger volume of code than the simple decision tree that you showed in your example.
Right. So the decision trees that we talked about, the largest one had 44 conditionals in it. And then for comparison, the largest neural network we were successfully able to prove things about had 4 nodes total. Because there's a lot of things that basically go wrong with neural networks. And part of the problem is that they divide the decision space with a lot of those angled regions, which then you have to have a bunch of rectangles to approximate them. And the other problem is that as you scale the number of variables in the network, you increase the dimensionality of the space, and that can lead to trouble with approximating the weighted volume with hyperrectangles. So it's just convergence is really slow, and yeah,
How do you get the population model in practice?
So in general, that's a good question. We can envision a future where companies, if they're using like machine learning models to determine whether to hire someone, have to prove that with respect to some government mandated population model, that those would have to be fair. For the purposes of the benchmarks, we took the same data set that we learned the models from and then just inferred Bayesian network-like structures.